Okay, so we're here for the last session of the day. So thank you all. So just as a small effort on our side, since you've been so patient to stay with us the whole day, I would like to tell you that there's an happy hour reception just after this session. So from 4:45 to 6. So I hope you can join so you can have like a relaxing drink after this all day of learning. So this is the last session in the serverless track. So just as a recap, we saw how you can develop and use the technology and grow your development team. We then saw how to apply architectural patterns to what you want to build with serverless technologies such as AWS Lambda. We also saw more recently how we can use global deployments with features like DynamoDB, so building global multi-region architecture, something that in the past would be really complex to and also very costly to do. The final session is the next step. So when you start to build large applications with Lambda, you start to have lots of functions. So let's see what we introduce over the years to help customers build this kind of complex serverless architecture. So normally, with a serverless app, you start with your first function. You are very happy. You link it to your events. And then you start to grow, and you have more functions that are coordinated in some way. Maybe this function triggers another function through S3, through DynamoDB, or even directly. And the number of functions grows. You can use SAM, but still there's maybe some functions that read and write from a database or some persistent storage. Maybe some function they receive information or send information to a queue where you can serialize your request. And sometimes you need to integrate your environment with legacy systems that are connected using Direct Connect maybe, and they are completely different architectures from the traditional architecture that you use when you build serverless technology. So there's lots of coordination here that it's something that you need to put into your code. If function calls that one, I need to wait for the result. What should I do if the result doesn't come in time? And normally, we saw lots of customers spending lots of time in this glue code instead of the business logic. And one thing that we said very clearly this year in the keynote with Werner Vogels in re:Invent was that our purpose is really to give you the tools so that you need only to focus on the business logic, maybe only write the business logic, and we then can take care of everything else that is around, that is the boilerplate code that is not giving you something different. So let's say that I want to build this kind of complex serverless architecture. What happens is that probably you can say one of these things, like I want to sequence my functions so that functions are executed in a sequence. And you can do that, but you need like every function must invoke the other function, so it's code that is running other code that is not really clean. You maybe you want to run some functions in parallel because they can get you the result faster. Maybe sometimes, depending on the data you have, you want to select a different function, and you don't want to write a function to do that. Sometimes you want to retry functions. I explained how we handle errors. So we basically have for asynchronous invocation, 2 invocations, and then you can write the DLQ, the letter Q. For synchronous error, we just give you back the error, and you should manage that. But maybe you have a function that is calling an external system, like a payment service that is outside of your control. What should you do if there is an error? How should you handle that? Maybe at function level, you just want to do something that in programming language is very common. You want to do a try, catch, finally. So I try to run this function. If there is an error, I want to catch the error. Finally, I clean my environment from everything that was created. And sometimes you want to run code not just for 5 minutes, but for hours. And you can do that because one function can trigger another function. There's in sequence or in parallel, you can do that. But still, it's lots of boilerplate code. So if we want, as AWS, help you, we can introduce a coordination layer. And this coordination layer needs to scale out because, of course, we are creating an architecture that can automatically scale. So we don't want to introduce a bottleneck. It needs to keep some sort of state. This is something that functions don't do. Functions They start with an event, and then they can return some value, but by themselves, if you don't store anything, they are stateless. If we create a coordination layer, maybe this layer can manage the state for the function. It can deal, as I said, with errors and retrials, especially if you call something that is outside of something that you manage, like a public API, or if you integrate your function with a legacy IT system that probably can't scale as well as functions, so sometimes it can be the bottleneck. And of course, this should be easy, otherwise you can already use functions, and auditable. So it means that in any point in time, this coordination layer should let you know what is happening, why it took this decision, why it started this task, and so on. So that's why we introduce step functions. They were introduced more than 1 year ago at reInvent, and then we saw our customer use them in ways that were completely different from what we were planning to. So we added more features. And the idea of this presentation is to introduce you how they work, and then we will review together after a demo some use cases that they were presented by customers to show how they were using step functions in production. So the idea with step function is that you can define a workflow, what we call a state machine. And if you studied computer science, this is exactly the state machine that you studied in computer science. So you define this state machine, this workflow that describes the task that you need to do, what should happen if something is passed through the different states. And you can use a JSON language to do that. And this JSON language is automatically visualized in the console so that you can really visually understand what you're mapping. And then if you execute a state machine, you can send some data, and then you can visually monitor the execution and every step from the console so that you can really understand and debug what's happening in a state machine. So this is the prototype hello world for a state machine language. You can have a comment. So as I said, it's JSON. Then you can have a comment. Then you have a list of states, and you have to specify which is the starting state. Here you have only a state, is hello world, so we start at hello world. Then the hello world state is a task that is using a resource, and there you can put the Amazon resource name or ARN of a Lambda function. So I'm not sure if you're familiar with ARN, but across AWS, we have this Amazon resource name syntax, ARN, that is a way to specify any resource inside AWS, so a policy, a role, and also any Lambda function. They have a unique way of being identified by this ARN syntax. And then, in this case, we have end true. That means that this state is the only state. It starts, and then it ends the state machine. So this hello world will use a task. So we will trigger a Lambda function that will do something, and then it will finish. So not very useful, but it's the simple example. It's important to say that when you use state machine, you can execute multiple state machines at once. So every state machine, you can run it once or up to 1 million of times in parallel. So scalability is very high. Of course, if you're using Lambda function inside, then you have the concurrency limit of Lambda that you need to change. But from the state machine perspective, there's the default limit is 1 million of parallel execution for every state machine. The maximum execution time of a state machine moves from 5 minutes with Lambda to 1 year. So a state machine can run up to 1 year. And you can also have waiting times, of course. You don't need to run code for 1 year, but you can create a workflow that can map a business process that takes, for example, days. An example of state machine that I like is the delivery. That's completely random since I'm from Amazon. The delivery process of if you buy something online, you create the order, you have to coordinate the delivery, then the parcel leaves. There's lots of waiting times, errors that can happen, and then should be recovered. So this is an example of a workflow that can run a few days, hopefully less than 1 year. Monitor execution from the console. This is an example of how from the console you can run a state machine. So you will see, and we will see a demo where we will really use the color to tell you in which step of the state machine we are. And if there is a branch or something, you will see where in the workflow we are going with this execution. And then at each step level, you can see the input and the output and the time of this single task. So each state of the state machine can be of these different types. So the task state is a unit of work that can be a Lambda function, or we will see later with activities, it can be anything running outside of Lambda, can be something running on EC2, something running in a container, something running outside of AWS, on-premise. It can even be just a human activity that needs to provide a feedback. So a task is really a flexible concept. We should think as a unit of work, and most of the times it will be a Lambda function, but it can be also something different. A state can be a choice where you want to add logic branching in your workflow. So if, depending on the state information that I receive, I can take a decision. So for example, the first task can be the payment is calling the payment service for your order, and then it can return that the payment was correctly received or not, because maybe the credit card didn't work. And then the choice state can be the next one, and depending on the state that it receives, you can take an action like, OK, I started the delivery, or I will signal that the payment didn't work, and you need to probably try another payment mechanism. If you want to run multiple things in parallel, you can use the parallel state. It will create two branches that are executed in parallel. So choice is you choose one branch or the other. Parallel will execute multiple states in parallel. And then you can reconcile these parallel states. And if one of the parallel branch will finish before of the other, we will automatically wait until all the branch will finish correctly, and then pass all the states as a list to the next step. A wait is used to wait for an amount of time or a specific date. So for example, you can have a wait state that tells, OK, you did some processing. Now I wait 30 seconds. 30 hours, or I wait a specific moment in time that can also dynamically computed, because maybe you know that something must happen before moving forward. Fail and succeed are two states that you can use to finish with an error or with a success the execution of a state machine. And pass is a state that normally does nothing. So it takes an input and gives out the same output. But since there's some manipulation of the state that you can do with the JSON syntax, you can use it to manipulate input and output in interesting ways. We will see a use case where this is done. So let's talk a little bit better of the tasks. So the task is the unit of work and can be a synchronous task. And the synchronous task is a Lambda function. So this is an example of a task that I call extract image metadata. It's type task. And then I give the resource of a Lambda function. In the flow of the state, you have an input state that is a JSON document, and then each state is passing their output as input of the next step. That means that this Lambda function will get in input the state. So the event of this Lambda function will be the input of this state, probably the input of the initial input or the input of the step just before this one. You can also have asynchronous task, and that's what we call activities. And activities work in a slightly different way. So they're used as a bridge with traditional IT or for human validation. So normally what happens is that you can create activity, and then when this activity receives something to do, there is a sort of a queue where all these things to do go, and then there should be a group of pollers that can be EC2 instance, container, or servers on-premise in another architecture that poll for something to do. So they will ask, is there something to do for this activity? When something goes into the queue, they will receive the input state. They can do their processing. It can be even human validation. And then they can say that this activity terminated correctly or with an error. And then the state machine can move forward. So in this way, you can integrate with anything outside. There's a very few APIs to integrate an external software as an activity. And I will show how that works in the demo. So those are the main APIs for activities. So you can create and register a new activity task. And then the nodes that are doing this activity, that, as I said, can be anything outside, even outside of AWS, they can poll for something to do. They can report their success or their failure. And if the activity is very long in time, like maybe it takes hours, you can optionally configure a heartbeat, so to tell that you are still working on this activity, so that if the state machine will not receive the heartbeat in time, like you say, every 30 minutes you should report an heartbeat, or every 20 seconds. If you don't receive the heartbeat, the state machine will assume that this activity failed, so it will reschedule the same input state with a new worker, a new poller node will receive the same state. So it's very robust and reliable because you need to report success or failure or a heartbeat, and otherwise the same work will be done by something else. Think like I want to process 1 million of images. I give this 1 million of images. You can have a group of instances that poll for things to do. They will receive this image, they process, they give the result. If they don't give the result in time, the same image will be sent to another node because we assume that the first time it failed in some way that we don't know. The language, the JSON language we use is called the Amazon State Language, and we publish under this link, and it's an open source language that we created, so everybody in the community, if they want to, we want to avoid to reinvent the wheel, so it's an Apache 2 license, so it's pretty open for anyone who needs a state machine or workflow language can reuse it. State machines are integrated natively with other AWS services. So for example, you can create dynamically state machine and activities from CloudFormation templates. You can invoke a step function, so execute a state machine from the API gateway. But this is an asynchronous invocation, so the API gateway can start a workflow, so a state machine execution, but then it can't wait for the result because it can take up to 1 year. So I don't think you want to build an API this slow. But even if it's very fast, it's just designed that you can just start the process, get the OK if the process started, and then you should have some other way to close the circuit. You can also use CloudWatch Events to trigger state machines. And this is interesting because all those IT use cases that we saw where I was suggesting maybe we can use a function instead of a script to run every hour and clean my snapshots and do my backup. If you want more robustness, you can replace those with a state machine that can eventually run one or more Lambda functions so that you can monitor retrials and everything. It's integrated with CloudWatch, so you have all the metrics. And it's integrated also with CloudTrail, so you have full auditing on the state machine execution. And most of the time, you use you can use also Lambda to trigger a state machine. So for example, you can have the API gateway trigger a state machine execution, but you have no way to manage the return status. So the return status will be our API return status. If you want to customize that, it's better to have the API gateway call a Lambda function that can trigger the execution of a state machine and then can return back any return status that you want with the syntax that you prefer. The idea is really to design visually. So you use JSON, but then you can immediately see how the workflow works. And so this is an example of a state machine that starts. So when it starts, you give an input state, a JSON document. For example, here it can be the link to an image that must be processed. Then you have extract image metadata. It's a task that triggers a Lambda function. The Lambda function will look for the image type. So this is a JPEG, this is a PNG, or maybe this is just binary. I don't think this is an image. And then you can give back the image type as a return state. This will go to a choice state that, depending on what is reported by the Lambda function, can say this is not a supported image type and fail, so a fail state. Or it can store the image metadata on DynamoDB and then run in parallel 2 branches. One is using recognition to look for what's inside the picture and extracting the tags. The other one is building the thumbnail of the picture, and maybe the output is the link to the S3 bucket where you store the thumbnail that you generated for the picture. Since these 2 branches are executed in parallel, when they both finish correctly, you will get a list state. So the state will be a list with all the return state of the parallel branches at once. So the list will contain the output tags and probably the link to thumbnail as a second value of the list. And at this point, you can finish correctly, or maybe report this information as output of the execution of the state machine. So you can do everything in a single Lambda function, but it's much more difficult to monitor. It's much more complex to manage errors if, for example, you have been throttled by recognition or DynamoDB. And it's also more complex to add new features if you want to add it, because you need to know the code. This is an example of how you can build a serverless human approval tasks. So the idea here is that we use the activities, but we don't need to run code. We just need a human to say yes or no to an activity. So in this case, we have CloudWatch Events that maybe once per day is sending some, is triggering a Lambda function. The Lambda function creates an activity task and then sends an email using Amazon SES. And this email is received by a client and can contain two links. That is like, I approve, I don't approve. And these links, they go both to the API gateway, and they are mapped to the send task success or send task failure for the activity. And this goes back to the step function. And clicking on the link of the email will go to the API gateway. The API gateway will send the success or the failure. So you have built a human approval task with basically without lines of code, if not for sending the email to the user. This is the same example that we already saw in this way in the previous presentation. And on the left, I just described the state machine, so how to do image recognition and processing. The idea here is that if we watch, we have two complete different approaches in how you can represent an architecture. Now, on the right, we have the architecture with the flow of the components. On the left, we have the state machine, so the workflow of how the data and the decisions and the branch that I need to run. So even if I like very much architecture, I think that the state machine is much clearer to me. If I need to build it, I know exactly what's the logic behind, what are the components. So I think it adds information to what you're doing. This is another example. It's also available here. And it's using CloudWatch Events to trigger some EBS snapshot management. So EBS is our block storage. It's our block storage when normally customers, they have their own process to create snapshots. When you create a snapshot of an EBS volume, usually it takes a few minutes. And then CloudWatch Events will fire an event that is the snapshot is completed. So normally nobody listens to this event, but you can connect a state machine that will get information every time the snapshot is finished. And this state machine can do this. So it can add a tag to the snapshot, so saying, OK, this has been done. It can count the snapshot for every volume and delete if there is more than n snapshot for a volume, so that you only take the last n snapshot of a storage device. And then it can finish. And it can also start to copy this snapshot in another region. So if you have a disaster recovery policy, you can say automatically, every time a snapshot completes, the state machine starts, it will tag, delete the old snapshot, and start copying the snapshot in another region. And in the other region, you can have something similar that will delete the oldest snapshot. So if you're interested in this kind of architecture, that's the link. And state machine are really interesting to build this kind of robust IT automation tasks. So let's see a demo, so maybe things are also clearer. So this is what I want to build. So if you were here in my first presentation, I already was playing with greetings and names. So let's move it a little bit more further. So I want to build a state machine where you give a name. This name must be validated, so it must be a correct name. The only correct name in the world is Danilo. Every other name fails. If the name is correct, then I say greeting with your name. Otherwise, I go to manage the invalid name. And then I can finish my state machine with the result. So these 3 points here, validate, invalid, and greet name, are 3 tasks that I'm mapping to Lambda functions. So let's go. No, we don't need to close this. Let's go here. This is the management console. Let's start with Lambda. So if I write here name, you see that I already have validate name, process invalid name, and greet name. These are 3 Lambda functions. So the validate name is, as you can imagine, is just looking if if there is no name in the input event, then this is an error. So there is a syntax that we suggest for every language. This is the syntax we use in JavaScript. There is, I think, at least a dozen ways to manage errors in JavaScript. So this is the one that we suggest to use. So if there is no name, I create a name error with a message that is no name. If the name is not in this validated list of names, then I have a name error with a wrong name. Otherwise, I just report that this ends correctly, and I just pass the input event as output. So I don't do anything. So I either raise one of these two errors, or I just pass through my input event. The process invalid name function is doing something very, very easy. So if I get the error as a cause, and then I look for the error message. If it's wrong name, I say, I don't know how to greet this name. If it's no name, please give me a name to greet. Otherwise, it's an unknown error, and then I report this message. And the final function that is basically almost the same as the first one that we did this morning, but without any check. If there is a name, I say hello name. If there is no name, but this should not happen, I say hey, and it's reporting this greeting. So we have these three building blocks. Let's build a state machine out of this. So let's go on the step function console. So here you have some templates, projects that you can use to learn. The templates are really interesting because show you lots of examples. So there is the hello world template. It's the same template that we saw before. So hello, it's not probably interesting. The wait state, I think it's interesting because it shows you how you can wait with step functions. So here you have like, I start at first state. This is the first state, is a task, is running some Lambda function. And then the next state is wait using seconds. Wait using seconds, so this is just a name that I use, is of type wait. It waits for 10 seconds, and then it goes to wait using timestamp. Wait using timestamp is of type wait, and that's a timestamp. This is an absolute time. This next step is nice, is wait using timestamp path. It's showing how we can start to use dynamic values in the state machines. So this is of type wait. It's timestamp path. And this syntax here is JSON path. So JSON path is a syntax that allows you to navigate a JSON document and extract information or eventually change information in a JSON document. So here I'm saying $ is the root of the JSON document. So starting from the root, there should be a property that is expiry date. Use the value of this property in the state as a timestamp that I need to wait. So that means that if I have a Lambda function that is doing some processing and you need that, then you wait for a specific event to happen, you can pass this as output of the Lambda function, and the state machine will then wait this time before going further. So you can map any business process that is not very fast, that has some maybe waiting for logistics, waiting for other actors to do something in this way. This other example is seconds path. So it's like the previous one, but instead of having a date, you have some amount of time in seconds to wait. And then you have a final state that is running another Lambda function. So this is telling you how the wait state works. Retry failure is the way you can retry a task. So this is the same hello world task as before, where I call some Lambda function. But then I can add a retry property to the state. And this retry property can have a list of different ways to retry this function. So first, you say you can catch the error. So if the error is custom error, then retry with an interval of 1 second, retry for 2 times, and apply this exponential backoff rate. So the exponential backoff rate is every time you retry, you multiply the interval by this value. And this is something that in Amazon we use a lot. Also, AWS does that. So it means that if you receive a peak of requests, and probably that can be a problem where the Lambda function fails, maybe an external provider was not capable of having this throughput, The first time you retry after 1 second, then after 2 seconds, 4 seconds, 8 seconds, you can really spread a peak of request into a large amount of time. The second one is catching errors, and you have different intervals, max attempt rate, and backoff rate. So you can really have catch different errors, and depending on the error, have different strategies. So for example, if you have an external API that fails, maybe you want to retry with an exponential backoff until the API works for lots of times. If you have an internal error that you know you can't solve, it's better maybe to fail immediately and report the error in some way so that someone can manage the error. So depending on the error, you can catch it. This states error here is error from the state machine, so like the task failed or any error from the state machine. These custom errors are errors that are raised by the code, like I did for the name error in the validate name function. Parallel, as the name says, is you have a task of type parallel, and basically you give, this is the next state when all the parallel branch end, is the final state. And then you have a list with multiple branch. Each branch is a list of states, and this will be executed in parallel. They must all complete correctly. When they all complete correctly, we wait here that everything completes. The final state will receive in input a list with all the returning value of the single parallel branch here. The catch failure is similar to the retrial, but instead of retrying the same function, you can start a different branch. And here you basically run a task. This is, again, a Lambda function. Then you catch the error. And depending on the error, you can have a different next state. So if the error is custom, you go to custom error fallback. If the task failed, go to reserved type fallback state, and so on. So you can apply different logic depending on the error you get. So it's really a catch, try catch. And the choice state is similar to the catch, but you don't choose depending on an error, but you choose depending on the return value of the previous state. So here you have the first state is a task, a Lambda function. The return value of this Lambda function, that should be JSON. You create a choice, and the choice will look, again, using JSON path. So if this JSON document has a foo property, and the numeric value of this foo property is 1, go to first match state. If the numeric value is 2, go to second match state. Otherwise, the default state is where you have to go, and so on. So you can really put your business logic here depending, and map it to different branch and choices depending on the return value for the different task. So now I want to create this from scratch, and I want to create the state machine that I was showing before. So this one should work. So this is the raw state machine. If I refresh here, you see that it's we start at validate name, then we catch a name error. If there is a name error, I go to invalid name. Otherwise, I go to greet name, and then there is invalid name and greet name that they both end the state machine. So this works, but you see there is no resource here. So if I click here, I automatically have the list of the functions that I can use. So this is validate name. So this is the ARN. Then here I have invalid name. So the function is called process invalid name. And greet name here, I should have a greet name function. OK, now this state machine is mapped to the right functions. And I can give it a name. So let's call it Builder's Day. And I can create the state machine. So now that it's created, I can run executions of the state machine. So that's how we call it. So normally invocation is for Lambda function, execution is for state machine. So I can create a new execution. And when I create a new execution, you have to give an input state. So let's give it a name. You know that the only valid name is Danilo. So I can start the execution. You see that this started. We're now in the validate name. The console is slower, so actually we probably already passed this state, but it gives you it takes some time to update. So the validate name worked well. We went to greet name, and then it finished. So here I have the information. I can see the input. It was name Danilo. And if I go to output, I get the output is hello Danilo from the greet name. If I click here in any state, I get the input and the output of every state. So validate name, in this case, didn't nothing because the name was valid. And here I gave also the list of all the tasks where I entered, where I started a Lambda function. I can click on to get the link to the Lambda console or to the CloudWatch logs of the Lambda function to see each step what happened. And I have the clear timestamp of what happened. So this is really important because it gives you the auditability that you need for a business process that can be mapped here. So let's try to run a new execution. So let's try with a wrong name. So Danilo with an H. So we are in the validate name. I can see that the input is this one. The output, we still don't have the input. Probably the function already terminated, but the console is a little bit slower to catch up. And then this time, the output was an error. We went to invalid name, and the output is I don't know how to greet the name. And even if I see the whole execution step, I see this is the input to the state machine execution, and the output is I don't know how to greet this name. Finally, just for fun, let's give an empty state with no name, and we go to invalid name again. And now the console is catching up. And in a matter of seconds, we should see, yeah, please give me a name to greet. And this is all the three possible use cases of this very basic state machine. But I think this can give you an idea of how you can map a business process and also how this state machine works. So what this service provides is storing the state up to 1 year. And each step is giving you the output of a step is the input of the next step, and is stored reliably across multiple availability zones. So you can have up to 1 million of this execution in parallel, and each one has their own state that is propagated. With state machine, you pay by the state transition. So the cost is very low, but you pay for every state transition. So it's not the invocation, but it's how many state transition you have. Normally, if you have a very complex process, it's more expensive than Lambda, but normally you use this not for everything in your website, but for very important business process. So for example, you have maybe a website where you are an e-commerce company, but when someone is buying something, then you need to start a business process that is checking payment, checking the availability of the product in the warehouses, starting the delivery, keeping the customer updated with the delivery. So this kind of things is what you would map here, not like a single invocation to a web server. So let's dive a little bit deeper into the activities to see how that works. So this is let's make it a little bit bigger. So I'm using the AWS CLI. It runs everywhere. It's written in Python. You can use it on Windows, Mac, Linux. And AWS step functions, you have access to all the primitives that I get here. And here I get create activity. So I can create this external task that you can use instead of Lambda function. And then here I can send that this task failed, the heartbeat, or this task succeeded. So since it's my last session, let's copy and paste because I don't want to do all the possible. So let's see if there are activities now. Currently, there are no activities, I think. So let's see list activities. There are no activities created in this region. So let's create an activity. And this activity, let's think this is an external validation. Maybe in your workflow, at some point, you need to connect and call a legacy system that is on-premise and needs to do something to validate your business process so it can run on AWS because you have something that is there for ages. So I create this external validation, and you see I get an activity ARN now. That is a unique way to identify this external validation activity. And now I can see if there's something to do for me. So let's see. So basically, I do AWS step functions. As I said, it's late. So step function, get activity task. So this is what the poller, so who needs to run this activity outside of the step function, should call to say, hey, there's something to do for me. And you have to pass the activity arn. And the activity arn is this one that was reported. So now this could be, for example, a group of servers running on premise, an auto-scaling group on AWS, or it can be even some software running on premise on a legacy software. Now there's nothing to do because this is a new activity. Nobody asked to run this activity. There's nothing to do. So let's see if we can use this. So you see, this is using long polling. So now I'm pending, waiting for something to do. How can we have something to do? We can go here and create a new state machine. And we can call it activity demo. And this state machine, let's see if I have it here. So for simplicity, I just create a state machine that has a single state. But again, you can create anything complex. So I have an external validation state. This is of type task. Here, now, as a resource, instead of passing a Lambda function, I pass the arn of the activity. So this is the way that the state machine knows this is not a Lambda function, but it's an activity. And then this will finish. This is similar to the hello world, but I have this external validation. I can now create the state machine. And still, if I go here, I'm still pending, nothing to do. Now I can trigger an execution of the state machine. I can send a comment like the day is almost over. Stay for the happy hour. So this is the input to my execution. And now if I go here, I see that something happened. Actually, this activity received something to do. This is the part. Basically, I get the input to my state, and is the serialized version of the input document, so the document. And then I get this task token. And this task token is a unique string that I can use when I reply to say this activity completed or failed, or there is an heartbeat. I use this task token to connect back. So what I can do, for example, if we look here, we see that this activity is still, this state machine execution is still going on. I have up to 1 year to reply. So now we can wait a few days. Now let's do it quickly. So let's go. So now, if I go back here, just to avoid reinventing the wheel. So basically, I can send a heartbeat with this syntax. It's not required because I didn't enforce that, but in my state machine, I can say, run this activity and ask for a heartbeat every 10 seconds or 30 minutes. And then if you don't receive that, the state machine will assume this activity failed, and I will make it available for another poller to start working on this. And here I need to give the old task token. So now I'm reporting the heartbeat. Nothing actually will change. And if you go here, we see that it is still running. Now I can report maybe a success. And I should use, usually make mistakes here with the syntax. So send task success or failure. Or better. This is the task output. It's a string that contains inside a JSON. So you need to escape all the characters. And here I can give back again my token. OK, and let's go here. And we should see the state machine. Yeah, so the state machine execution terminated. And if I go in output, I see the result OK is what I passed here. So in this way, you can integrate with any legacy software. It's really a few lines of code or a few lines of script, because you can use the AWS SDK instead of this CLI. Or you can use this for manual validation. It's really the way to extend beyond simple Lambda functions. And it's, for example, if you have an integration with an external system that is sending you messages, you can very easily wrap this into this kind of command so that you can get validation that moves your business process forward from external notification, from a payment service, from a delivery service. So if you have your e-commerce business process, maybe if the delivery service you're using is sending you messages through any web or non-web architecture, you can take this message and then wrap this into this syntax so that your state machine will say, OK, the parcel has been delivered to the customer. OK, so this was the more technical part. So now let's see some case studies, because maybe now we start to understand how they work, but lots of people can say, why should I use this? So this is a few customers that shared their stories at re:Invent last year in December. So this is Coca-Cola. So Coca-Cola, I think, only in the US. I'm not sure if they have this overseas. They have like an application where you can get credits when you buy drinks. And then when you have credits, you can get a free drink. So this is amazing marketing. People is very happy. The problem is that sometimes they get like, I know if I get another Coke, then I get a free one because I reach my limit. But then they go and the application, then they pass the barcode of the application. It says, no, sorry, you still don't have credits. So they have this, the number of credits was getting out of sync. And this was giving a very bad customer experience, as you can imagine. So they discovered that the problem was that they use a payment processor that was talking with a legacy consumer database, and the legacy consumer database was much slower than the Lambda functions they were using. So what happened is that the consumer database was saying, OK, I paid. So they were sending a refresh of the state. But when they were reading back the information on the consumer database, even if the payment was correctly gone, it was still not updated because this legacy application was slower. So they just added a state machine that is waiting for, I think, 90 seconds before reading the updated value. So before, when you were going out of sync, there was no way to sync back because you need another payment to resynchronize this process. So the customer was getting a wrong credit value. Now they wait for 90 seconds, and then they update the credit value, and they know that the consumer database is updated by then. So it takes 1.5 minutes, but now they have it. And even if it's very simple, for them it was much easier to do that than to add any other loop and stuff. This is Thomson Reuters. So Thomson Reuters, if you know them, they basically sell information. And the speed of they can provide you information, especially for the financial market, is important. And part of this is videos. So they needed to transcode videos. And to transform 350 videos clips per day into each of those was to be transformed into 14 different formats. So it takes some time to do that. They were using ffmpeg. It's an open source tool to do that. And normally ffmpeg, it takes the same time to do the transcoding as the length of the video. So that means that they were quite slow in providing the videos. From when they received the video, and they have all the 14 formats for 350 clips available, it was not the best experience. So basically, they found out that with ffmpeg, you can find the keyframes inside the video. The keyframes are the full frames that are part of a video encoding. Normally, most video encoding, they put keyframes, and then for some time, they put the delta, the difference, and then when the difference is too much, they put another keyframe, and that's how MPEG and most video encoding works. So it's very fast with ffmpeg to process the whole video and extract only the keyframes. So they use this to split the video into much smaller parts, and then they process all these smaller parts that usually are something like 1 second or half a second in parallel to do the encoding, and then they join the video back. So in this way, they could move the encoding of a video from 20 minutes to 2 minutes, running all the Lambda functions in parallel. And since you pay mostly by the duration, the cost is the same, because instead of running lots of Lambda function in sequence, you just run them in parallel. And this is how they work. So basically, they have all these prepare sleep, split prepared, perform sleep, sleep performed, prepare poll, wait for results, and then they give the comments back. So it looks a little strange. By the way, this is a nice trick they use. So inside the Lambda function, you have very little storage. You have a /tmp that is 512 megabytes, and it doesn't grow. It's there. It's reused if we recycle the container, but it's not we can delete it in any time. So basically, to process, they use ffmpeg to process the videos, and then they send the output straight to the command line interface. And the AWS S3 command line interface can take standard input in Unix and send it straight to S3. So basically, they don't store the video on disk, but they use a traditional binary, and they take the output, send it to S3 using the CLI as a stream, and it's then written into this file. So this is a nice trick. If you need to write an intermediate file, because then you need to upload it to S3, you can just use this streaming architecture. And this works also in input. So this is the standard Unix syntax. The dash means standard input or standard output. So this is copy standard input to this file. If you switch the dash here, it would mean copy this file to standard output, and then you can add a pipe and process information. So this is a nice trick to use memory instead of storage, but still you need the memory to host the file. And then they decided when we have to run like 100 or 1,000 Lambda function in parallel, we don't want to do that inside the state machine because it would be complex. So basically, they use S3 as a trigger. So the state machine will write 100 segments, each an object. Each file will trigger a Lambda function that will process this small portion of the video file. And then they have another Lambda function that will wait for all this Lambda function to complete. When everything has completed, we'll join back the file. So this is a nice trick, because otherwise, with the JSON syntax, you don't have the dynamic way of launching multiple branches. You need to hard-code the number of parallel branches. In this way, they put this outside of the state machine. And this is the syntax. Just to give you an idea, they manipulate the state in an interesting way. So they start with an init here. It's of type pass, and pass means that you do nothing. But they manipulate the input state, and they take the result path here and the result, basically saying take the JSON object that is the dollar. This is JSON path, so dollar means the root. In the root, take the operation that can be there and put prepare split. So prepare split will be the value of the operation in the state and pass to the prepare split state. And if you look here, the Lambda function is always the same. They're always using a single Lambda function, because this Lambda function will look in input for the operation, and depending on the operation that it receives, it will do different things. So if the operation is prepare split, it will prepare the split of the file, so look for the keyframes. Then it will, when the split is prepared, they will change the operation to perform split, and then they call the same Lambda function, but the operation now is perform the split, so it will do the split and write to S3. This will go to split performed, and then it will wait for results, and it will enter in a loop. I don't enter into all the details because it's quite tricky, but the idea is that they have a multiple state where they arrive and they look for a poll status, and they have a choice. So if they arrive here, and the poll status will be just submitted, and then they go to loop waiting using seconds. Loop wait using seconds will wait 3 seconds and then call a Lambda function. The Lambda function will look at if all the encoding of this 100 function has completed. If it has completed, it will will change the state to complete. Otherwise, it will change the state to progressing. So it goes back here, and we'll see it's complete. No, it's progressing. Go again here, wait 3 seconds, call the Lambda function. And then at some point, the state will be returned by the Lambda function complete, and then it will go to servlet complete state. And here, it will change the operation to concat, to concatenate all these small videos. And then it will go to the complete state, where the final Lambda function will take this video and will send it to the video shipping service that will send it to the customer. So it looks a little bit strange, but it's how you can build a loop and wait for something external. They chose 3 seconds because they really wanted to minimize the time when everything finished. So they did quite interesting things. I think the most important is that they could easily scale to 1,000 concurrent Lambdas if they need it, just for a few seconds, and then they shut down. Doing the same with 1,000 EC2 instances, it would not be as fast. It would be much more costly and complex to manage. So they can really scale as much as they want and shut down in a matter of seconds, and they only pay for the hundreds of milliseconds that they use. This is another customer, is frame.io. So frame.io is, again, doing videos, and they are in the business of review and collaboration of videos. And they say, I want to use Lambda, but sometimes my videos are long. I don't want to do the splitting. So they simply want to choose. If the video is long, I use containers with ECS. That's the other track. If the video is short, I can use the 5 minutes of Lambda. I can do the encoding. So they have like this workflow. We have the encoder decider that will choose if they want to run ECS or the Lambda encoder. And then at the end, they have two success or fail states that are shared by the two different parallel processes. And they just use, when they get in input, the state as an asset property that has size and duration. And depending on the size and the duration of the video, they run the Lambda encoder or the ECS encoder as the next state. And then, if we look at the code, there is like, they have this, in case they run a container, we found that they retry for 720 times every 5 seconds. That's an hour, I think. And we understood that basically what happens is that when they submit jobs to their container cluster using ECS, sometimes the cluster is out of resources. There's no available resources. The cluster will auto-scale, but usually it takes some minutes. So basically, they use this simple loop to say, OK, if there are no available resources in my container cluster, I will wait for auto-scaling or resources to get freed. So I just retry every 5 seconds. And then when there is the resource, the container with the encoding will trigger. And then they have like the final part, I think here. When they finish, they use, again, CloudWatch Events. So CloudWatch Events normally is triggered by events inside AWS, but you can use it as a message bus if you want, or an event bus. So they use this to communicate, and they have other business process that will listen for these CloudWatch events, custom events that they create to continue and do and use the video. So this is the other use case. So if really can't stop liking state machine, this is the link where you should go. This is where we have a few tutorials that you can follow along with the console. So the image recognition example that I did multiple times over the day, there's a nice tutorial that tells you how to build it. So if you want to get practice, it's nice. Also the EBS snapshot management, they're both at this link. And finally, since we discovered customer using state machine in a completely different way that we expected, this is the hashtag. So if you use state machine, just tell us what you do on this hashtag. The service team is really following this hashtag, and they're looking for what customers are doing and ways to improve the service based on your feedback. And with this, I think this very long day of serverless technology is coming to an end. We're starting the happy hour in a minute in the other room where the lunch was served. I hope you can stay. But even more, I hope you enjoyed the day. I hope it was interesting, and happy to get your feedback. Thank you.